The power of lead-acid batteries is essential for our everyday lives. They are reliable and affordable, powering our cars, storing energy for our homes, and backing up critical equipment. Their widespread use highlights their importance in various applications. Lead-acid batteries have been around for over 150 years, making them a well-established technology. Their longevity speaks to their reliability and effectiveness. Understanding how these batteries are made provides insight into their robust design. The manufacturing process involves several steps, each crucial to creating a functional and efficient battery. From raw materials to final assembly, the process is carefully controlled to ensure quality. Let's delve into the fascinating world of lead-acid battery production. Lead-acid batteries, as their name suggests, rely on two primary raw materials, lead and sulfuric acid. Lead is a heavy metal known for its softness and malleability, making it ideal for forming battery components. Sulfuric acid, a highly corrosive liquid, acts as the electrolyte, facilitating the chemical reactions within the battery. Lead is sourced from ores found in various parts of the world. The most common lead ore, galena, undergoes several processes to extract and refine the lead metal. Sulfuric acid production involves a chemical reaction between sulfur, oxygen, and water. The quality and purity of these raw materials are critical for the performance and lifespan of the battery. Impurities in lead or variations in sulfuric acid concentration can negatively impact the battery's ability to store and discharge energy effectively. Therefore, strict quality control measures are implemented throughout the manufacturing process. The journey from raw lead ore to usable lead for battery components involves several steps. The first step is mining the lead ore from the earth. This ore is then crushed and ground into a fine powder, increasing the surface area for subsequent processing. The powdered ore undergoes a process called flotation, where chemicals are added to separate the lead from other minerals present in the ore. This concentrated lead is then subjected to smelting. Smelting involves heating the ore in a furnace to melt and separate the lead from remaining impurities. The molten lead, now significantly purer, is poured into molds to create lead ingots. These ingots are the building blocks for the battery components. The purity of the lead is crucial at this stage. Impurities can affect the battery's performance and lifespan. Therefore, the smelting process is carefully controlled to achieve the desired lead purity for battery manufacturing. The battery's internal structure relies on a framework called a grid. These grids are typically made of lead alloy, which is a mixture of lead and other metals like antimony or calcium. These alloying metals enhance the grid's strength and corrosion resistance. The manufacturing process begins with melting the lead alloy. The molten alloy is then poured into molds and subjected to high pressure. This creates a thin sheet of lead alloy with a specific pattern of holes or grids. These grids serve as the support structure for the active material that will be applied later. The design and thickness of the grid play a vital role in the battery's performance. A well-designed grid provides a large surface area for the active material, allowing for better current flow and increased battery capacity. Section 5. Paste mixing, creating the active material. The active material is the heart of the battery, responsible for storing and releasing energy. For lead-acid batteries, the active material is a paste made by mixing lead oxide powder with sulfuric acid and water. This process requires precise control over the ingredients and mixing conditions to ensure the desired paste consistency and properties. Two types of paste are made, one for the positive plates and one for the negative plates. The positive paste typically uses lead dioxide or PbO2 as the primary lead oxide, while the negative paste uses lead oxide or PbO. The paste is carefully applied to the grids created in the previous step, filling the spaces between the grid structure. The paste's density, porosity, and adhesion to the grid are crucial factors that influence the battery's performance and lifespan. Section 6. Plate curing, transforming the paste. Once the paste is applied to the grids, the plates undergo a critical step called curing. Curing involves controlled drying and chemical transformation of the paste. During curing, the plates are placed in a controlled environment with specific temperature and humidity levels. This process allows the paste to harden and adhere firmly to the grid structure. Moreover, curing initiates chemical reactions within the paste, converting the lead oxides into the electrochemically active materials required for battery operation. The curing time and conditions are crucial for achieving the desired paste characteristics and ensuring optimal battery performance. After curing, the plates are ready for assembly into a complete battery cell. Section 7. Battery assembly, putting it all together. The cured plates, both positive and negative, are now ready to be assembled into a battery cell. A battery cell consists of alternating positive and negative plates, separated by a porous material called a separator. The separator prevents the plates from touching each other and causing a short circuit. These plates and separators are stacked in a specific sequence with positive and negative plates alternating. The number of plates in a cell determines the battery's capacity. More plates mean higher capacity. The stacked plates and separators are then inserted into a battery case, typically made of polypropylene, a durable and chemically resistant plastic. The case provides structural support and insulation. Once the plates and separators are in the case, a cover is sealed onto the case and the battery is filled with electrolyte solution. Section 8. Initial charging, activating the battery. The assembled battery, though physically complete, is not yet functional. It requires an initial charge to activate the active materials and make the battery ready for use. This initial charge, also known as formation charging, converts the lead sulfate present in the plates into the electrochemically active materials needed for energy storage. During this process, a controlled current is passed through the battery for a specific duration. This charging process converts the lead sulfate in the positive plates into lead dioxide and the lead sulfate in the negative plates into metallic lead. This transformation establishes the electrochemical potential difference between the positive and negative plates, enabling the battery to store and discharge energy. Once the initial charge is complete, the battery is tested for voltage, capacity, and other parameters to ensure it meets the required specifications. Section 9. Conclusion. The significance of lead-acid battery production. The production of lead-acid batteries is a multi-step process that transforms raw materials into reliable energy storage devices. Each stage, from lead processing to final charging, plays a crucial role in determining the battery's performance, lifespan, and safety. The precise control over materials, processes, and quality checks ensures that the final product meets the demands of various applications. Lead-acid batteries continue to be essential in various sectors, from powering our vehicles to providing backup energy for critical infrastructure. Understanding their production process sheds light on the complexity and ingenuity behind these seemingly simple yet powerful devices that play a vital role in our electrified world.